Hello, my dear students. Today we are going to continue chapter 3, which is chemical equilibrium. We are going to discuss the ionic equilibrium, and we are going to discuss the different types of substances that conduct electric current, which are called electrolytes and non-electrolytes. And we are going to show experiments about the conduction of electric current, and we are going to discuss some problems on them. So let us start. Ionic equilibrium. First, we have to know the types of the solution. Solutions can be divided by conducting electric current into two types: non-electrolytic solution or non-electrolytes. It means solution which don't conduct electricity, and we have given reason in this point. Because their solution are free from ions, so non-ionized, for example oils, kerosene and sugar solution, as the following animation will show. My dear student, as shown on the screen, if you bring sugar solution and you are going to connect it to source of electric current and lamp, you will find that the solution does not conduct the electric current and the lamp does not light. This means that sugar is non-electrolyte, does not contain ion solution in the water. My dear student, we are going to show another experiment to show the non-electrolyte solution. On passing electric current in pure acetic acid dissolved in benzene or hydrogen chloride gas dissolved in benzene, we will find that the lamp will not light in both cases. We have given reason in this point because they are not ionized, so neither of the two liquids contain ions, thus don't conduct electricity. So the conclusion for this experiment: the solution of pure acetic acid or hydrogen chloride gas in benzene is non-electrolytic solution. Now, the second type of the solution, according to conduction of electric current, is the electrolytic solution or electrolyte. It is a solution which conducts electricity, and so we have given reason in this point. Because this solution contains free ions, positive and negative ions. So we have two types of electrolytic solution. Strong electrolytes, which completely ionized in their solution, like strong acids as hydrochloric acid, sulfuric acid and nitric acid, and strong alkalis like sodium hydroxide and calcium hydroxide. And weak electrolytes, which are partially ionized in solution, weak acids as carbonic acid and hydrocyanic acid and organic acid, for example acetic acid, and weak alkalis like ammonium hydroxide and aluminum hydroxide, as the following animation will show. Here, if we bring water and we put it in a beaker and we are going to dissolve hydrogen chloride gas in it, we find that it ionizes completely into hydrogen ion and chloride ion, and the hydrogen ion combine with water forming hydronium ion. So the ions here produced make the conduction of electricity is very good, and so the lamp lights brightly, and so it is a strong electrolyte. Now, my dear student, if we put acetic acid in the beaker, we find that the lamp does not light brightly like the hydrochloric acid. Why? Because the acetic acid is weak electrolyte and partially ionized in water, so the lamp does not light brightly like hydrochloric acid. So it is weak electrolyte. Now, my dear student, we are going to discuss the ionization process. It is the process in which the unionized molecules are changed into ions. The complete ionization, it is the process in which all unionized molecules are changed into ions. As the equation proceeds on the screen, if we bring molecule which like AB, two elements here, capital letters, they are ionized completely into A positive ion and B negative ion. Here, for example, hydrochloric acid changes into hydrogen ion and the chloride ion and other strong electrolytes. Here, the second type of ionization, which is the incomplete ionization. Here, it is the process in which the small ratio of unionized molecules are changed into ions. As the equation proceeds on the screen, AB, which is weak electrolyte, here it ionizes partially into A positive and B negative. So it exists in equilibrium with its molecules. For example, acetic acid and other weak electrolytes. Now, my dear students, we are going to define what do we mean by ionic equilibrium. It is the equilibrium arises in weak electrolytes between non-ionized molecules and their ions. So we have good reason in this point. Ionic equilibrium arises only in weak electrolyte because the solution of the weak electrolyte contains free ions and non-ionized molecule. As shown on the screen, AB molecules exist in equilibrium with their ions, A positive and B negative ion. So we have good reason in this point, my dear student. Ionic equilibrium does not arise in strong electrolytes because their solution are completely ionized, so contain free positive and the negative ions only. As the equation proceeds on the screen, AB strong electrolyte, all the molecules are ionized into A positive ions and B negative ions. Now, my dear student, we have to show the experiment that shows the difference between the strong and weak electrolytes. On passing the electric current through equal concentration of 0.1 molar hydrochloric acid and 0.1 molar of pure acetic acid. The observation here, in case of hydrochloric acid, the lamp gives a strong illumination, and we have good reason for this point. Because it is completely ionized, so containing large number of ions, so good conductor of electricity. As the equation proceeds on the screen, hydrogen chloride gas, when it dissolves in water, it forms hydrochloric acid, and the hydrogen ion produced combine with water molecule forming hydronium ion, and the chloride ion is released. In the case of acetic acid, the lamp gives faint or weak illumination, and we have good reason in this point. Because it is partially ionized, so containing a small number of ions. As the equation proceeds on the screen, acetic acid plus water, it gives acetate ion and hydronium ion. Here the ions exist in equilibrium with the acetic acid, and small ratio of molecules are ionized into acetate ions and hydronium ion. Here, the second step, my dear student, on dilution of both solutions to 0.01 molar, then to 0.001 molar, and test the conductivity of electricity again through both of them. We find that the observation here, the illumination of the lamp is not affected by dilution in case of hydrochloric acid, and we have good reason for this point, because it is completely ionized in its aqueous solution. As the equation proceeds on the screen, the hydrochloric acid that dissolved in water, it ionizes into hydronium ion and the chloride ion completely, while the illumination of the lamp increases by dilution of acetic acid, and we have good reason in this point. Because according to Le Chatelier principle, the ionization of acetic acid shifts forward direction on adding this amount of water, so the unionized molecules are ionized gradually. As the equation proceeds on the screen, acetic acid plus water, all the molecules that acetic acid here are ionized by adding excess amount of water in forming a state ion and hydronium ion. On adding extra amount of water, more molecules will be ionized into their ions. Here's the conclusion, my dear student. The solution of the acetic acid or hydrogen chloride gas in water is electrolytic solution, such the hydrochloric acid is a strong electrolyte, while the acetic acid is weak electrolyte. So we have good reason in this point, my dear student. There are no positive hydrogen ion or protons in the solution of acids. So my dear student, here the answer, because when the acid is ionized in water, the positive proton is linked or combined with water molecule through coordinate bond to form hydronium ion, H3O positive. As the equation pursued on the screen, positive hydrogen ion combined with water to form hydronium ion. My dear student, notice that the law of mass action is applied only in case of solution of weak electrolyte, and we have good reason for this point. Because weak electrolyte solution contain undissociated molecules and their ions. My dear student, the value of the ionization constant Ka for different acids is constant at constant temperature, and it differs from weak acid to another. Weak acids differ in the degree of their ionization, as the degree of ionization equals the number of ionized moles over the total number of moles. Now, my dear student, we are going to discuss Ostwald's law. It shows the relation between the degree of ionization or dissociation of weak electrolyte and its dilution. And it states, at constant temperature, when the dilution increases, the degree of dissociation increases. So, on dissolving weak electrolyte or weak monobasic acid like HA in water, it partially ionizes as the following equation. HA gives HA positive ion and A negative ion. Here, my dear student, at equilibrium, the ionization constant Ka equals the concentration of positive hydrogen ion times the concentration of A negative ion over the concentration of the acid HA, where H positive, A negative, and HA are in concentration of the resulting ions and undissociated molecules of acid. My dear student, as very small ratio of acid is ionized, as the acid is weak, so the number of ionized moles of HA equal alpha. So the number of unionized moles equal 1 minus alpha. So the number of H positive moles equals the number of A negative moles equal alpha. So as the equation proceeds on the screen, the number of moles of HA before dilution is 1, but on adding ionization of the weak acid, so small number of moles are ionized, so equal alpha. So 1 minus alpha is the remaining, and the hydrogen ion and A negative will be alpha molecules. So if the weak acid is dissolved in volume V of liter of solution, we find that the concentration of HA equal the number of moles over the volume, 1 minus alpha over V, and the concentration of hydrogen ion equals alpha over V, and the concentration of A negative equal alpha over V. So the equilibrium constant Ka equals alpha over V times alpha over V over 1 minus alpha over V, so equals alpha square over V times 1 minus alpha. So as the ionization of the weak acid is weak, so the degree of ionization alpha is neglected. Thus the value 1 minus alpha equal 1. So Ka equilibrium constant equal alpha square over V. And as K equal alpha square over V equal alpha square times 1 over V, so the concentration of the weak acid C equal 1 over V, so we can write Ostwald's law, Ka equal alpha square times C. Now, my dear students, we are going to discuss some problems. Calculate the degree of dissociation of 0.1 molar solution of HCN at 25 degrees Celsius, given that the equilibrium constant of the acid Ka equal 7.2 times 10 to the power negative 10. Solution of the problem: Ka equals alpha square times C as Oswald's law. So 7.2 times 10 to the power negative 10 equals alpha square times 0.1. So alpha square equals 72 times 10 to the power negative 10. So alpha equals 8.5 times 10 to the power negative 5. Second example, calculate the equilibrium constant for the dissociation of 20% of hydrogen iodide at 356 degrees Celsius. Solution: as the equation proceeds on the screen, 2Hi gives H2 plus I2. As we know the number of moles of the Hi as the equation proceeds, 2 moles. So the number of dissociated moles of hydrogen and iodide, which is 20%, so equal 20 over 100 times 2 equals 0.4 moles. Then the number of moles of hydrogen equals the number of moles of iodine equals 0.4 divided 2 equals 0.2 moles. And the number of unionized moles of Hi equal 80 over 100 times 2 equal 1.6 moles. So by applying the equilibrium constant Kc for the reaction, H2 times I2 over Hi power 2, so 0.2 times 0.2 over 1.6 power 2 equals 0.0153. Another example, calculate the concentration of hydrogen ion and hydrogen sulfide ions, which is the degree of dissociation in 0.1 molar H2S solution at 25 degrees Celsius, given that the equilibrium constant equal 8.9 times 10 to the power negative 8. Solution: as the equation of Oswald's law applied, Ka equals alpha square times C, so 8.9 times 10 to the power negative 8 equals alpha square times 0.1. So alpha square equals 8.9 times 10 to the power negative 9. So alpha equals 9.4 times 10 to the power negative 5. Next example, calculate the ionization percentage of 0.1 molar acetic acid, given that its ionization constant equal 1.8 times 10 to the power negative 5. Here the solution: Ka equal alpha square times C by applying Oswald's law. So 1.8 times 10 to the power negative 5 equals alpha square times 0.1. So alpha square equal 18 times 10 to the power negative 5. So alpha equals 0.013. So the percentage of ionization here equals alpha times 100. So equals 0.013 times 100. So equal 1.3%. Next example, if the degree of dissociation of weak organic monoprotic acid is 3% in 0.2 molar solution, calculate the ionization constant Ka for this acid. Solution of the problem: alpha equals 3 over 100, so equal 0.03. So Ka equal alpha square times C. So Ka equal 0.03 power 2 times 0.2. So equal 1.8 times 10 to the power negative 4. Now, my dear students, we are going to discuss the calculation of the concentration of hydronium ion H3O positive for weak acid or the positive hydrogen ion. As acetic acid is weak electrolyte and it is ionized in water as the following equation: acetic acid plus water gives acetate ion plus hydronium ion. At equilibrium, Ka equal the concentration of the acetate ion times the concentration of hydronium ion over the concentration of the acetic acid. each mole of acetic acid ionized into 1 mole of hydrogen ion and 1 mole of acetate anion. So the concentration of acetate anion equals the concentration of hydronium ion. So we can write the equilibrium constant Ka is the concentration of hydronium ion power 2, as they are equal the concentration of acetate ion and hydronium ion over the concentration of acetic acid. So the acetic acid here is weak acid. So the number of moles of dissociated acid moles is very small. So they can be neglected. So we can say the concentration of acetic acid at equilibrium equal its original concentration equal C. So Ka here equal hydronium ion power 2 over concentration of the acid C. So hydronium ion equal square root Ka times C. Now we are going to discuss example for calculation of hydronium ion. Find the concentration of hydrogen ion in the solution 0.1 molar of acetic acid at 25 degrees Celsius, given that the equilibrium constant for the acid equal 1.8 times 10 to the power negative 5. Solution. The concentration of hydronium ion equal square root of Ka times C. So equal square root of 1.8 times 10 to the power negative 5 times 0.1. So equal 1.342 times 10 to the power negative 3 molar. Now, my dear students, we are going to discuss some questions. The first type of question is write the scientific term. The maximum water vapor pressure in air at certain temperature. If you think about it, yes, it will be saturated water vapor pressure. The pressure due to water vapor in air at certain temperature. If you think about it, my dear student, it will be vapor pressure. Next point is the change in concentration of the reactants per unit time. If you think about it, yes, it will be rate of chemical reaction. Is apparently stationary state, but in reality it is dynamic. If you think about it, yes, it will be equilibrium state. Second type of questions, choose the correct answer. The equilibrium system involves what type of process? Identical, simultaneous, reversible, B and C. If you think about it, yes, it will be B and C. Next point, reaction of hydrochloric acid with magnesium is complete reaction. As what? It occurs at high temperature, it occurs under high pressure, there is an equilibrium between reacts and the products, hydrogen gas is evolved. If you think about it, yes, it will be hydrogen gas is evolved. Next point, the solution of acetic acid and ethanol turns blue litmus paper to red. As what? As ethanol has no effect on litmus, equilibrium is established, reaction is reversible, and acetic acid is still in the reaction solution, or both answers B and C are right. So my dear student, if you think about it, yes, the answer it will be both answers B and C are right. Now, my dear student, we have given reason. Heating cylinders of butane from outside is very dangerous, because heating process converts the butane from the liquefied state to the gaseous state. As a result, the volume of the gas increases and causes high pressure on the cylinder walls, leading to its explosion. Catalyst does not affect on the reaction equilibrium, because it increases the rate of both forward and backward reaction by the same proportion, so it decreases only the time needed to reach the equilibrium state. So it reaches equilibrium fast. Complete or irreversible chemical reaction occurs in the direction of formation of products only. We have to say, because one of the products escapes from the medium of the reaction in form of gas or precipitate. That's why the products cannot combine with each other to reform the reactants. Incomplete or reversible chemical reaction occurs in two directions. We have to say because both of the reactants and the products are found in the medium of the reaction. That's why the products can combine with each other to reform the reactants again. My dear students, we have reached to the end of our program today. I hope you understood all the points and different types of problems that we discussed today. So till we meet again, my best wishes for you.